Okay, the time is 4 o'clock in Central Europe, or I don't know, wherever you are. And I think we'll begin now. So we are very happy to have Benjamin Keisling with us from Lamont-Doherty Earth Observatory. And he will talk about, past as a prologue, how archives help us predict the fate of Earth ice sheets and the future of our discipline. So a very cool talk, I guess. Benjamin?
Thanks so much. Thanks everyone for having me. Good morning here from the States and good afternoon and evening to those of you in other parts of the world. Really happy to be able to share some of my work with you all today. I want to start today by amplifying the work and the words of a student group at Columbia University, natives at CU. The Lenape lived here before and during the colonization of the Americas. We recognize these indigenous people of Manhattan, their displacement, dispossession, and continued presence. This acknowledgement stands as a reminder to reflect on our past as we contemplate our way forward. And this is an important concept for me too to think about, as much of the work that I'll be talking about today focuses on Kalaalleq Nunaat and the ice sheet that resides there. Indigenous Greenlanders have lived alongside that ice sheet for thousands of years and continue to do so today. So as we talk about the million-year history of this place, I think it's important to remember too that there's a really vibrant and ongoing living history to engage with as well. Today, I will share with you a brief presentation that will start with a little bit about my trajectory into the work that I do now. And then I'll share two vignettes with you. The first one about the processes that have shaped the Greenlandic landscape in the past and some ongoing work to try to better understand how Greenland will evolve in the future. And then I'll share a bit of my work on the landscape of our discipline and the processes, particularly in the United States, that shape what the geoscience looks like today and how we can change those processes to make our discipline look different in the future. In general, the themes of my research focus on how ice sheets respond to climate change, and in particular, understanding the processes and mechanisms that have driven ice sheets to change in the past. One thing that I'm also very interested in is how we can use geologic archives of the past behavior of the ice sheet to better contextualize the observations that we're making today and to better predict how the ice sheet might respond to climate change in the future. In order to do this work, I primarily rely on numerical ice sheet models, which I couple with climate models, reanalysis or idealized forcing, and importantly, I strive to always be integrating my work with geologic archives so that there's a conversation and back and forth between our idealized numerical models and the information that we have from the geologic record about what actually happened on Earth. For those of you that don't think about ice sheets all of the time, I like to talk about this schematic because even as someone who does think about ice sheets all the time, I still find it very helpful to think about the processes that affect an ice sheet. So an ice sheet is a large glacier that rests on solid land. The characteristic aspects of an ice sheet can be described mostly with what's called an equilibrium line, which is the elevation at which the amount of snowfall that occurs during the course of a year is matched by the amount of melting that occurs during the course of a year. So at the equilibrium line, the change in mass is zero because those processes balance out. There are two zones of the ice sheet. There's an ablation zone where melting exceeds snowfall and an accumulation zone where snowfall exceeds melting. And because the ice is so heavy and deforms under its own weight, the ice sheet is able to vacate mass from the area that's in the accumulation zone to the ablation zone, resulting in the flow lines that you see idealized on this diagram. There are other processes that affect the ice sheet as well. There are interactions with the ocean where the ice sheet is floating or directly calving into the ocean. And there can be other processes like solid earth feedbacks. And I highlight these major processes because thinking about all of these processes is an important step towards setting up and running the kinds of numerical models that I do. The first process that is really important to capture is understanding what's the climate that the ice sheet is experiencing at any given time. And in order to do that, I also run numerical climate models. There's an example of a numerical climate model on the right-hand side of this graph. You'll see RACMO 2.3, that's a reanalysis product. And then to the right of that, the RCM output is a regional climate model that I've run for a modern day configuration of the ice sheet. We do this by first running a general circulation model at a coarse resolution. We then save output from that model every 6 hours, which is used as a boundary condition for a Greenland only domain. And I'm showing you this modern calibration of the regional climate model to show you that we don't perfectly capture Greenland's climate today, but we get a lot of the major features of what the climate looks like. So a really cold central dome, as well as a cold southern dome in temperature space. And then in terms of precipitation, we see the highest rates of precipitation along the southeast coast and a very arid north and northeast Greenland. It's important that we capture these broad patterns because the power of being able to run a climate model like this for forcing the ice sheet is we can also run the same model for ice sheet configurations that look very different from the configuration that we have today, so that the climate doesn't have so much memory of the ice sheet being there. In terms of the ice sheet model that I run, it's usually a three-dimensional thermodynamic ice sheet model called the Penn State ice sheet model. It uses a approximation for ice flow that's called a hybrid shallow ice, shallow shelf approximation, with those domains coupled across the grounding line where the ice transitions to floating, using a parameterization for the flux developed by Christian Schoof in 2007. And then we also use parameterizations for ocean melting, calving parameterization, and a basal sliding law that depends on the strength of the basal material and the thermal state of the bed of the ice sheet. So in terms of running the model, what I like to think about is, models are always going to be an imperfect description, an incomplete description of reality. But what's really important when we're using models to address scientific questions is to ensure that we're including the processes within our model that are necessary for answering the scientific question that we're asking of it. And so in general, the way that modeling works, we think of a physical process, we come up with a mathematical description of it, which we then implement in a discretized fashion in a computer code, and then we can use that computer code to test hypotheses and run experiments about how the ice sheet would respond to different kinds of perturbations. And I've put on below here some examples of different processes or mechanisms that, depending on what we were studying, we would want to ensure were included in our ice sheet model. So before I get into the research I want to talk to you about today, I want to provide just a little bit of a sense of a trajectory of how I got to where I did, because I didn't wake up one day and just start ice sheet modeling. I'm originally from Portland, Oregon. I went to do my bachelor's degree in physics at a small college in Minnesota, St. Olaf College. And I didn't know it at the time, but as an undergraduate involved in research, I actually got my first experience with numerical modeling. I was doing really simple 1D flowline modeling to understand the distance that ice that fell as snow 10,000 years ago had flown downstream. And I found this really fascinating to be able to apply my physics knowledge to studying Earth systems, but I had never taken a geoscience course. So I went in to do a PhD in geoscience. I actually started working in an organic geochemistry lab, and I completed my master's on a project from a lake in northeastern Siberia, Lake Elgegikin. This was my first experience actually working in a wet lab, and I learned a very important lesson that the wet lab was not where I wanted to spend the rest of my scientific career. I really missed the computer-based work that I was doing as an undergraduate. And so for my PhD, I transitioned back into working with more numerical methods, and in particular working on ice sheet models with my supervisor, Rob DeCanto. I had the opportunity also to spend a year as an exchange student during my PhD working at the Center of Ice and Climate, now PICE, in Copenhagen. And some of the work that I started there is what I'm going to share with you today. Now I'm a postdoctoral research scientist at Lamont-Doherty Earth Observatory of Columbia University, and I continue to broadly be interested in past periods of ice sheet change as analogs for both what we see today and what we'll see in the future. So to get into this research project now, I'm particularly interested in the Greenland ice sheet because for as long as we've been observing what the Greenland ice sheet is doing, we know that it's been losing mass. This is an animation from NASA that covers the time period from 2002 to 2016. And we can see that although there's a strong spatial pattern in terms of where mass loss is occurring, there's also a really pronounced downward trend in what is happening to the ice sheet. And when we look to the geologic record, there are very intriguing examples of time periods when we think that this kind of mass loss probably went all the way to its logical ending and the ice sheet was reduced to almost nothing, just a very small footprint. And so this graph is from a Nature paper published in 2016 by Jurg Schaefer and others, where they measured cosmogenic nuclides in the bedrock beneath the thickest part of the Greenland ice sheet, beneath where the GISP-2 ice core was drilled. And what they found is that the concentration of cosmogenic nuclides, which are only accumulating in these rocks when they're exposed to the open atmosphere, the concentration of those nuclides was so high that the ice sheet had to have been away from that site sometime in the past about 1.1 million years. And they proposed a number of different hypotheses for when the ice sheet would have been gone. And those are summarized in these red and blue bars. So the red being time periods where they proposed the ice sheet was gone, and the blue being time periods where they proposed the ice sheet was covering central Greenland. And below that is the marine isotope stack from Lisecki and Ramo, where they're able to sort of tie or conjecture which of these certain periods in the past may have been the ones when the ice sheet was missing or had melted. Now, this paper came out when I was a visiting student in Copenhagen, and it really excited my office mates and I because we were already thinking about what did Greenland look like in the past, and this observation presented a really interesting conundrum. When the ice sheet is gone, what does Greenland's climate look like? And when Greenland's climate is adjust to having no ice sheet, how do you actually grow an ice sheet? What are the sort of glaciological dynamics and implications that could help us understand the differences between these proposed histories? And so the first thing that we had to do to address that question is actually run a climate model to understand what would Greenland's climate look like before there was an ice sheet. And so in the ice sheet model, we melted away the ice sheet and we allowed the bedrock to isostatically rebound to a pre-glacial equilibrium bedrock. And from there, we were able to calculate the climatology using a regional climate model for what the climate would look like under a pre-glacial conditions. And so here's a comparison between that same modern climate that I showed before with a different scale bar, and then a pre-glacial climate. And what you can see is that in terms of temperature, we really lose the footprint that the ice sheet leaves on temperature when we melt away the ice sheet. There's actually about there's about 16 centimeters of sea level equivalent in this pre-glacial Greenland. We've allowed there to be some mountain glaciers in southeast Greenland to account for the fact that there's pretty robust evidence that there was some ice delivering ice rafted debris to the North Atlantic from Greenland, even before there was an established ice sheet. But what we can see in terms of precipitation space is that losing the ice sheet really makes precipitation throughout Greenland more regular. So you lose the strong asymmetry that we see with the ice sheet today. And then we used this pre-glacial climate. We wanted to use this to understand, okay, so what are the dynamics of glaciation now? How does the ice sheet nucleate? How does the ice sheet grow? What does that look like? And in order to do that, we wanted to come up with a simple way to describe glacial interglacial cycles in terms of the climatology without having to constantly rerun the climate model, which is takes a lot of time and is computationally laborious. And so what we did is we thought about, okay, what are the major features of the Milankovitch processes that are causing climate to change during the sort of Plio-Pleistocene, this time period when we know we've gone from having no ice sheet to having some kind of ice sheet. And we came up with a description of climate during this time that's based on 3 independent parameters so that we could run ensembles with different forcing and understand if the response of the ice sheet was the same. And so we came up with this idealized way to describe the climate using 3 things: standard deviation of interglacial temperatures. So sometimes you have particularly warm interglacials, like we saw highlighted in that Schaefer plot before. Standard deviation of glacial temperatures. So we know that glacial periods tend to be more extreme than interglacials, but are also variable. And then a rate of long-term glacial cooling. So as the Northern Hemisphere was becoming more glaciated, did we cross a threshold that might have influenced the behavior of the Greenland ice sheet? And for this modeling, our motivation was really to understand the feedbacks between the growing ice sheet, the solid Earth response through that GIA process that we're capturing, and the changing climate. So this evolution of the climate system from the Pliocene and into the Pleistocene. So we ran our ice sheet models with these idealized forcings and an ensemble approach. And along the bottom graph, you can see how this new Greenland ice sheet starts to grow. And so this is what the ice sheet looks like as we're going from a pre-glacial state into a glaciated Greenland. And so now below our idealized temperature forcing, I have plotted the ice volume in meters of sea level equivalent. There's a black horizontal line there at about 7.4 meters sea level equivalent, which is the modern volume of the ice sheet. And so what we see is in these simulations, which run for 1.2 million years, we see the ice sheet going from basically no ice sheet on the far left of this graph at time equals 0 to an ice sheet that oscillates between very small and modern. And then as the climate gradually cools, we actually transition to a kind of mode where the ice sheet is oscillating between modern at its smallest and then a sort of glacial size, so up to 12 or even 16 meters of sea level equivalent at its maximum. And we can see that not every glacial interglacial cycle is the same. In fact, sometimes we skip interglacial periods when the ice sheet is able to survive in interglacial. And sometimes we have a very strong response to interglacial forcing going from a large ice sheet. So particularly here around 900,000 years into the simulation, we go from having a very big ice sheet to a very small ice sheet. And as we were analyzing the simulations, we saw something that was really striking, that as this ice sheet was growing, when it got very big and when we transitioned from one of these large glacial ice sheets to a reduced interglacial ice sheet, we actually ended up with a big proglacial lake on the landscape. And this was particularly pronounced during these kinds of transitions that I just mentioned. So from a glacial size ice sheet to when there's a strong interglacial following the development of a large ice sheet. So it's sort of this spontaneous combination of a couple of the different parameters that the solid Earth has had time to adjust to there being a really large ice sheet, but then a particularly warm interglacial follows that, and it elicits a big response from the system. And so what I'm showing in this third plot is the volume of a proglacial lake that develops in central Greenland. And we are going to look at that now spatially, so you can see what these lakes look like. And this is what we found, that during these large transitions, we actually end up with ice dammed lakes that are below sea level. in central Greenland. And so this plot is showing two different time slices that are highlighted on this graph at the top, this lake volume graph. And then in the spatial maps, I'm first showing just the size of the full ice sheet with the ice sheet on top of it. And the ice is transparent so that you can see what the bedrock looks like. And all of those blue and purple colors are area below sea level. So because the ice sheet has gotten so thick, we've actually depressed this large region in central Greenland below sea level. And then there's a hydropotential flow line that is drawn on top of that. And that hydropotential flow line is actually calculated from the second plot that I'm showing here. And so that's the starting from an outlet in northwest Greenland, where the we calculated the water routing on all of these surfaces. And basically that red line is starting from the outlet that is calculated by that water routing algorithm. What is the sort of primary direction along which water is going to flow on this landscape? And we found that depending on the configuration of the ice sheet, that hydropotential flow line could either lead to northwest Greenland or northeast Greenland via those feedbacks between what the solid earth is doing and what the ice sheet is doing, and how that creates the landscape that the water then responds to. So here I'm showing one of these simulations during a time period where we get this response that we found emerging from our models, this development of a big proglacial lake. And it's pausing at the point when the proglacial lake is towards its biggest size, so that you can see not only 2D, but also in terms of a cross section of what the ice is doing. And so that here, that red is a profile of the ice sheet. And then you can see the bedrock beneath it. And then in blue, that's the proglacial lake that develops. And you can see it's an ice dammed proglacial lake that sits on this landscape as the ice sheet is retreating. And so we were really interested in the implications of this mode of retreat for the landscape. And we, of course, were intrigued by the fact that our water routing was leading to an outlet that today is associated with one of the most spectacular canyon features on Earth, the Peterman Canyon, that runs about 750 kilometers from Greenland's northwest coast at the Peterman Glacier outlet to honestly near to the point where, near to central Greenland, to the point where the GISP 2 ice core was drilled. In any case, we were interested in thinking about how much erosion potential this amount of water on the landscape would have. And so we did this in a couple of different ways. We looked at similar magnitude flooding events that have been actually observed. And then we also predicted a spillway erosion rate using an equation that we found in the literature. And from our back of the envelope calculations, using what we were able to derive from these simulations in terms of the sill height and the lake surface height, as well as using outcrops around Greenland in northwest Greenland to get a sense for what the erodibility of these basement rocks would be. We came up with a back of the envelope calculation that suggests erosion rates on the order of 0.5 to 5 meters per year for one of these big flood outburst events. And as I mentioned or foreshadowed before, what's really intriguing about this is that precisely in Northwest Greenland, we have a very large, very spectacular canyon feature that has actually been argued to be fluvial in origin, because we have this strong and characteristic V shape throughout the morphology of the canyon. And so although it's clear from the morphology that this has been eroded by water, the actual mechanism for how this canyon emerged and what may have deepened it over time is something that we don't know a lot about yet. So these simulations have allowed us to put forth a new hypothesis that rather than simply fluvial erosion being responsible for this canyon, interactions between the growing ice sheet, the solid earth, and the meltwater that those processes can leave behind during glacial interglacial cycles results in a large amount of water left on the landscape that can perform the work of this erosion in a setting that is still glaciated or being influenced by ice sheets. And in order to try to confirm this hypothesis, there are a number of already existing lines of evidence that are consistent with our theory, as well as new emerging ones. I'll just highlight one here. The last time that there was a coordinated ocean drilling expedition in Baffin Bay that was led by the Ocean Drilling Program was in 1989. And their northernmost site was site 645, which you can see on the left-hand side here in the center of Baffin Bay. They found a unit of Pliocene-Pleistocene age that they described as consisting of sharp-based, unburrowed, muddy sands to sandy, silty muds that we believe to be ice rafted on the basis of shipboard description. The sharp bases, lack of lamination, and lack of burrowers all suggest rapid emplacement of poorly sorted sandy sediment. And so there are many of these units within the subunit 3A that they observed as sort of these discrete events. And there was also some provenance work that was done at that time showing that the source of some of those grains was unique to Northwest Greenland, to rocks that had been observed around Thule. And so this was exciting because in addition to ice rafting, or perhaps complementing ice rafting, we think that this also could be evidence of the sort of discrete meltwater flood events that would be consistent with the mechanism that we describe. And I just want to give a shout out to Paul Knudts and others in Denmark and others throughout the world that have proposed a new drilling expedition in Baffin Bay that would hopefully take place in the coming years to get much more detailed information and new cores from the area right offshore of Northwest Greenland that could help us directly test the hypothesis we propose here. So to conclude this part of the talk, we propose a new testable hypothesis about solid Earth ice sheet interactions during the time period when Greenland was becoming glaciated. I mentioned before the work of Paul Knudts and his leadership in putting together a new drilling program that could help us even further explore these questions. I also want to highlight a recent work by Guy Paxman and others who discovered a Paleo lake basin beneath Northwest Greenland. And future work to study that basin might actually allow us to describe the paleoclimatic and paleo-environmental conditions that would be able to test the theory that we propose in terms of the number of subaerial exposures and the processes that were occurring on the landscape, things like that. We think that glacial lake outburst floods, like the ones that are shown in this animation, are a plausible mechanism for the formation of one of the longest canyon features in the world. And these floods also have implications for understanding the role of the growing Greenland ice sheet in other kinds of Plio-Pleistocene climate change, for example, for forcing some millennial scale climate changes during the Pliocene that have been observed in other records, but we've sort of lacked a plausible explanation for because of outstanding assumptions about the stability of the ice sheet. And so this is a mechanism that could actually provide a way to synthesize all of those data in a realistic way. Now, I just want to give a bit of a teaser and preview as well for some ongoing work that I am doing as part of my postdoc. We recently were funded by the National Science Foundation to lead a project that's called Green Drill. I mentioned before that this rock core from central Greenland that Jörg Schaefer measured cosmogenic isotopes in, that really inspired and shifted a way of thinking about the ice sheet for me that led to the work that I just presented. In Green Drill, we have been funded to drill through the ice sheet and collect samples of subglacial bedrock throughout northern Greenland in order to test hypotheses about which sectors of the ice sheet are most prone to change in the future. And the way that this is going to work is we're actually going to drill transects from currently unglaciated terrains up to 300 to 600 meters ice thickness, so that we can collect bedrock samples that help us map out the spatial footprint of the ice sheet during the last time periods when it was smaller to today. So another way to sort of look into the past of the ice sheet as an analog for thinking about what our future might hold as melting around Greenland continues to accelerate. And so for this green drill program that I hope you'll be hearing more about in the coming years, we've had some fieldwork pauses, but those are certainly temporary. I'm leading a modeling effort to actually directly integrate cosmogenic nuclides into our ice sheet models so that we can run long integrations like the ones I showed you before, but actually directly predict the accumulation of cosmogenic isotopes in the bedrock beneath the ice sheet in a way that can account for all of the processes that affect the accumulation of these isotopes, like the elevation of the bedrock surface, which changes through time, and erosion of bedrock, which can remove these isotopes. And on the right-hand side is just a preview of some of that work, showing in the dark colors the accumulation of these nuclides. In addition, we have a really exciting opportunity with Green Drill to develop bedrock boreholes as natural laboratories for understanding complementary Earth system processes like geothermal heat flux, or understanding more about the provenance of different terrains in Greenland and how they link with the exposures that we can see around the coast today. So now I want to move into the second vignette part of my talk, and I am aware of the time, so I will keep it moving. Just to say, what I love most about being a scientist and the kind of work that I get to do is the sense of discovery, of learning actually new skills to pursue questions that are really interesting to me, and also collaborating with people who have complementary interests, but look at those problems from different angles. And I want to share now another story about discovery for me that has been very influential to the work that I do. And it also has a lot to do with landscapes, so that's really fun. When I was a graduate student, I was a mentor for a group that was called OSTEM. Out stands for Out in STEM, so a group mostly for LGBTQ plus undergraduates. And one day, one of them asked me, who is a LGBTQ role model in geosciences for you? And I realized I didn't have an answer for that question. I literally didn't know any. So I started doing what I do best, research. And I learned about someone whose story now I really like to share because his work has really motivated me. His name was Dr. Clyde Werhoftig, and this is recorded so you can come back. I encourage you to learn more about him. He was a glacial geologist and worked a lot in California on the glacial history of Yosemite. But a story that I learned about him that was really influential was that he actually won the Distinguished Career Award from the Geological Society of America in 1989. And he was 70 years old at that time. And during his acceptance speech, he used that opportunity to come out to his colleagues as gay, which he had never done before. And that, to me, was a very, apparently it was pretty controversial. I've heard from people that were there that people were leaving the room. But for me, it was really encouraging to hear. And what I learned from that is that you shouldn't be afraid to do things just because no one else has done them before. And that often the things you want to do have been done before. And studying the past can give clarity and purpose to your efforts. And so I want to give a couple examples of how these specific lessons have motivated some of the work that I've done in this space. And I'll do so quickly as we're running out of time. When I was a graduate student, I was very interested in using the skills I had developed to read scientific literature to actually apply that to reading literature on diversity, inclusion, and pedagogy. So we started a reading seminar that's still running today. And that actually, some of us in that group, that led to a publication, a peer-reviewed publication in GSA Today for us. I also was very involved in sort of community-based efforts to create meaningful spaces for graduate students, particularly graduate students of color in the UMass community. And we created a program called Bridge, which I would encourage you to read more about in a paper we published in EOS called What's in a Seminar. The other thing that I learned about when I was engaging with the history of Dr. Verhofstadt is that he was actually a participant at a conference that was really surprising to me to learn that it happened, called to the First National Conference on Minority Participation in Earth Science and Mineral Engineering. And this conference happened in 1972. There were over 300 participants from over half of the US states. And there was a really clear focus on the barriers and opportunities and strategies for broadening participation in geoscience. And this conference was organized by Dr. Randolph Bromry, who was then, at the time, he was the chancellor of UMass Amherst and one of 4 Black scientists in the United States to have a PhD in geoscience. What's been really interesting to me to learn more about this first national conference is that I think it problematizes some of the assumptions that we tend to make about the geoscience community and the processes that shape it. And so I want to offer some reflections on how engaging with this historical document helps us to move past those assumptions. So the first assumption is that this topic of diversity, equity, and inclusion is a niche interest that's not interesting to everyone. And if you look at who participated in this major conference in 1972, I think that's clearly not the case. Most folks, I think, regardless of where you are, you might recognize the NASA logo. US-based people might recognize a lot more of these as well. There was a really big buy-in from the federal government. There was a lot of industry representation and industry partners thinking about their role. And I want to note that historically, industry has played an outside role in creating pathways into geoscience that serve the needs of diverse populations. There were a lot of academic institutions. I was surprised to see a number of institutions that I've attended on this list when I compiled it, even though I had never heard that they participated in this really important example of brave leadership in our field in thinking about how to make the geosciences more just. And then finally, there was actually a really big cohort of folks who didn't know anything about geoscience, but actually came from a civil rights background, who brought their expertise in thinking about race and the processes that influence the social landscape in the United States, and contributed that expertise to these geoscientists that wanted to do something about that in their field. And for me, this really pushes back at the idea that studying the Earth and being vocal and active in advocating for aspects of social justice, that those two things are necessarily distinct. In this example from 1972, I think we see them as deeply and intimately connected. The document from this first national conference, it's about 180 pages that are typewritten, and it's something that I really encourage all earth scientists to engage with, because I think it's an important part of the history of our discipline, right? We think a lot about the history of this planet. I think it's also important we engage with the history of the way it's been studied. And there were amazing, when you read this document, you're also just gonna have a lot of really cool experiences, because there were some really amazing people that participated in this conference who were leaders in the civil rights movement in the United States, who shared some anecdotes that and perspectives that I think still really resonate with the work that we have left to do today. In terms of the United States, we know that since 1972, so over the period since the conference until the present day, we've still struggled as a discipline to become more welcoming for particularly non-white geoscientists. And this is true at the national level, so the graph from Bernard and Cooperdock on the left, but also at my own institution. We recently completed a report on the demographics of Lamont and found that these same processes occur at our institution as well. And I often hear this cited as a reason why the geosciences are further behind all of the other STEM disciplines, and that it's going to take us longer to address this gap. But engaging with the history of our field has actually made me see that from a different angle, and has made me see that within geoscience, we actually have a very distinct and a very visionary legacy with respect to broadening participation. And that has led me to think about, what are we going to do now to address this outstanding problem that we still haven't fixed? And what I see from looking at what they did really well, I think, at the first national conference, is that they built coalitions that connected undergraduate students and graduate students all the way up to chancellors and US senators, and engaged not only industry and academia, but also religious groups. So there's this really broad coalition building in support of their goals. I think what this has also shown me is that the political moment impacts geoscience. So 1972, coming right out of the civil rights movement, there was a lot of momentum to address broader questions of social justice. And the geoscientists at that time took that as an opportunity to say, hey, we have work to do in our own backyard. Let's think about how these processes are affecting our landscape. Lastly, this idea that change is necessarily going to be slow and that we just need to wait longer, that's not supported by the historical record, because we've been having the same conversation for 50 years. And so that change, we haven't seen it in 50 years. And I don't think it's reasonable to expect longer than that. And in the end, what I've learned is that none of the conversations that we're having around making the geosciences a more inclusive and just place are new. And we already have a lot of ideas how to fix it. And something that my collaborator and colleague said is what I carry with me now when I think about doing this work. She said, what this shows us is we have no choice left but to be brave. And so a project that I'm currently leading to try to apply these observations to changing and shaping the geoscience landscape in the future was recently funded by the NSF as an EAGER award. This project is called Alliance Building Offshore to Advance Resilience and Diversity. And we are looking at the role of leadership in advancing justice in geosciences and trying to cultivate leaders among the geoscience community in folks who range from undergraduate students to deans in the US system. Our team includes geoscientists, geoscience education experts, and folks with expertise in geoscience diversity. The model for All Aboard is heavily influenced by another program that I've been involved with, which is called STEMCs. It stands for STEM Student Experiences Aboard Ships. And if anyone knows any undergraduates in the US, I would encourage you to send them this website. STEMCs is open to all undergraduates in the US, even especially those actually that aren't studying oceanography or geoscience, because it's an opportunity to introduce students to the ways that their skills can be applied to thinking about the Earth and the ocean and glaciers. There's a picture of a trip that I led some students on to see a glacier in Alaska. What we've found on STEMCs, so STEMCs actually takes undergraduate students aboard US fleet research vessels during time periods when those vessels would otherwise be empty and transiting between sites. And what we found is that these environments, these field settings, they're not only really good for doing research and asking scientific questions, they're also really good for creating environments of mutual respect, creating spaces where you can build trust among cohorts and develop a sense of shared values. And frankly, at least from the US perspective, not all of our the mechanisms that we use to take people into the field are really places where safety is the top concern. And there are a lot of bad stories about people who make others feel uncomfortable or unincluded or hurt in conducting this kind of field work. And so we're thinking about how do we take these opportunities to go to sea rather as being places where we put up and tolerate a lot of bad behavior, but instead as crucibles where we can nurture the kind of leadership that the geoscience community needs to really meet our goals in the coming century. And so the way we've structured this program is we actually have 4 teams of 4 different people that span the undergraduate to the dean level at 4 US institutions. And by doing this, we've created a model where we're using a transformative offshore experience and connecting intergenerational teams in order to complete a leadership and resilience training and build coalitions that can broaden participation in the geosciences through their leadership. And so during All Aboard, we're building on some past work sessions that we've run at national meetings to equip folks with tools for excellence in this space, as well as providing sustained support for 4 institutions that we feel are really on the precipice of making the change to capitalize on that existing momentum. And through the program, we'll be developing metrics for the efficacy of these trainings, as well as thinking about how these efforts can translate to major seagoing vessels like the JOIDES Resolution in order to make those environments as inclusive and really safe and fun for everyone that participates. And so thank you all very much for your patience and sticking with me this long. Today I shared with you 2 vignettes, one about thinking about the past of Greenland and what that means for understanding what the ice sheet is doing today, and also thinking about the landscape of our discipline, the processes that shape it, and how we can shift those going forward. And with that, I want to say thank you to the many collaborators, co-authors, mentors, and colleagues, and combinations of those things that have helped me in my journey, and thank my funding sources as well. And I'm happy to take questions now, or you can always reach me by email, keisling@ldeo.columbia.edu. Thanks.
So thank you so much, Benjamin, both for the scientific talk and also all the diversity and additional knowledge, which I found, of course, very interesting. The chat is open for questions, and we have some questions. If anybody else also wants to ask in person, you can write an X in the chat or just raise your hand. But I'll start. We have 3 questions from Trevor Faulkner. It says, thank you for the fantastic modeling. And number 1, will you repeat for, I hope I'm saying this correctly, Fennos-Canadian ice sheet? Fennos-Canadian ice sheet. 2, are you aware? Yeah, sorry. Yeah. Are you aware of abstract by Ragnall et al. From EGU 2001 about many IDLs on FIS during deglaciation? And the 3rd question is, will you determine the sub-ice geology of Greenland from your boreholes? So feel free to answer at your own pace.
Yeah, absolutely. Thank you so much, Trevor, for these questions. I'm gonna save the chat. 1, will we repeat for the Fennos-Canadian ice sheet? That is not work that we are doing right now, but I think that would be really interesting to do in the future. And what's really cool, particularly about the Fennos-Canadian ice sheet, is you have a lot of these like really spectacular landscapes, and many of those also have this combination of glacial and fluvial processes that have influenced them. I think that it's slightly different because what's unique and interesting about the Greenland example and what motivated us to start there is that ice sheet is still on the landscape. And so it's interesting to think about what are the processes that has led to what we see today. But doing a similar kind of modeling for the Fennos-Canadian would definitely be a cool thing to do in future work. So thank you for asking that. I am not aware of the abstract, so that's an easy answer, but I've now saved the chat so that I can look it up because that sounds really interesting and related to the work that I'm doing. And then, yes, we will determine the sub-ice geology of the places where we get boreholes. And one of our hopes is that by having more like calibration points beneath the ice sheet, we can then use other methods like gravimetry, in order to better map out the ways that what we see today, the exposures around the margin, the way that those translate inland. Because a lot of people have done that work, great work before, using different parameters like the magnetic anomalies, gravimetry, but this will allow us to have even more sort of calibration points that go further into the ice sheet to strengthen those kinds of reconstructions. And we'll also be looking at geothermal heat flux and the presence of any sediment. For me, in modeling, those are two parameters that I'm really concerned about all of the time. And so it'll be great to have more examples of what those are beneath the present day ice sheet as well.
All right. I also want to say thank you, Benjamin, for this great talk. And thank you also for spending some of your time on these crucial issues on diversity. I think that's really important. But I'll just now highlight the next question in the chat from Jesse Sondervan. I enjoyed seeing the work on the beryllium-10 accumulation and ice sheet coverage. Now I wonder how this work with the ice sheet eroding the bedrock during the ice cycles of growth and melting. How do you expect this to work in the future?
Yeah, that's a really great question. And that's actually one of the reasons why it is so powerful to be able to do these comparisons directly between a physical model and the observations that we get beneath the ice sheet. Because in my model, I actually am parameterizing erosion. So the parameterization I use right now is based on whether the ice is frozen or if it's melted at the base. And then if it's warm based, the sliding speed multiplied by erodibility parameter. And of course, so that relates to the previous conversation about like, how do you actually map out what kind of bedrock it is? But in general, we can account for the process of erosion. And so that gives us another way to be calibrating and training the model on the data sets that we're able to retrieve from the bed of the ice sheet. What previous people, so in that observation from central Greenland, the Schaefer 2016 paper, they were able to measure a couple different samples in this bedrock core and create a depth profile. And they could fit a curve to that depth profile to actually back out the maximum amount of erosion that could have occurred. And they found that that was about 1.5 meters maximum. And so in doing future measurements, we're also going to be measuring depth profiles so that we have that same capability to try to back calculate the amount of total erosion that's occurred. In the modeling world, we're going to be continuing to just include that process and think about different ways that we can constrain the uncertain parameters in that. And so another just example, we do lose this bedrock that is really hot with cosmogenic nuclides because of erosion, but that material also ends up somewhere. And so others, Paul Bierman, for example, also in 2016, looked at the accumulation of cosmogenic nuclides in marine sediment as a sort of tracer of ice dynamics upstream. And so I think that's still not very high resolution compared to what we're able to model. But I think that in the future, we'll also be able to look to other places, not just sub-ice bedrock, but also the sink, where that eroded material ends up, as another way to get more at the process that you're asking about. So preservation is a problem, but we have ways to solve it. I could have just said that. Thanks for your question.
I think I just check if Jesse has a follow-up question here. I think it's just a comment, but maybe I can come with a follow-up question, because what we usually do for the cosmogenic nuclides, when it involves ice as well, we do inverse modeling to test, many different scenarios to fit the observations. And it's sort of the same thing that Schaefer he did, but just showing at least only 3 of them in the paper. How intensive or computationally challenging would that be for you to do enough of an ensemble of models to really check all the scenarios that could fit the data?
Yeah. I mean, there are infinitely many scenarios that fit the data. So the answer is it's just not possible. But I think that we can do a reasonably good job of describing like the possible parameter space that the Earth history exists in, and then run enough models that fill that parameter space so that we can get a better sense of the most likely scenarios for the past. And so one of the things that I'm doing right now that I think the ice sheet model is really powerful for is trying to understand, if you know that one particular location is ice-free, what is the probability, given that that location is ice-free, that another location is ice-free? And so we're using ensembles of models with different forcing to ask that question and kind of create a map of, for every site where we might have an observation that the ice sheet is gone, does that have a big impact on other places where we think, would have a strong correlation with when one site's gone, when ice on one site is gone, ice on the other is. And so we can't like run every single possible, realization of what could have happened in the past. But instead, what we're trying to do is kind of come up with ways to leverage the strengths of the ice sheet model, which is having that comprehensive description of the glaciology and the ability to describe multiple different processes that are coupling together, leveraging that in a way that helps us get at sort of the main uncertainties in that unlimited solution space.
Yeah, thanks.
Yeah,
sounds
question.
Really interesting.
All right, so I'll read the next question from our chat, which is from Maxime Bernard. Regarding the influence of bedrock topography on ice sheet dynamics, have you been interested in modeling the influence of fjords development and to what extent they played a role in Pleistocene shift in the glacial interglacial cycles?
Really good question. I haven't done that in the past, but that is absolutely a direction that I would like to go in the future. I mentioned this 2019 study by Paul Knutz, where they looked at the shelf and they mapped out the structure of different units on the shelf, which the continental shelf off of Western Greenland, and showed that there's just some potentially interesting changes in ice dynamics associated with changes in climate and the landscape during the Pleistocene. And I think that we really could do more to connect those observations with the glaciological modeling. Like I showed in the work that I already did, you have these kind of like distinct modes of glaciation as the climate system is evolving. And so really understanding how those different modes are potentially being expressed in the sedimentary record, I think would be a way to answer that question of how is the fjord development influencing the sort of dynamics of glacial interglacial cycles in this really critical period of Greenland's evolution.
Well, I think unless anybody else has any more questions in the chat, I think that's it. Oh, just thank yous. All right. So thank you very much, Benjamin, for your great talk, and thank you everyone who came and listened to us. Make sure you also listen to we also have some really great speakers coming up. We have Tamara Pico next week. So make sure you you follow up. And thank you, everyone.
Thanks so much for having me. It was really fun.
All right.
Thank you.
Thank you.